Calculus AB, Notes 1.7, the Intermediate Value Theorem. This is the second theorem that I believe that we've had so far this year. We had the limit existence theorem. Now we have the intermediate value theorem. And I think I'm going to take this opportunity to make this a little bit different in our notes and make it a little more clear. But let's read this. If f is continuous on the closed interval AB, that means that the interval has endpoints that are included, and f of a is less than y, which is less than f of b, then there exists at least one value, x equals c, on AB, such that f of c equals y. Now that sounds complicated. It is not complicated. Let me give you a picture to show you how not complicated this is. Take some random function, like so. We're going to take a point here. That x value is a. We're going to take a point here. That x value is b. So here's what this is saying. The y value, when the x value is a, of course, is f of a. Evaluate the function at that x value. The y value at x equals b is f of b. So to use the intermediate value theorem, the question is going to be, let's say that, let me throw some numbers in here, because right now you're thinking this is not any easier. Let's say that this is the ordered pair 7, 10. Just an example with numbers. This is not actually part of the theorem. Let's say this is 2, 3. First of all, according to the intermediate value theorem, for this theorem to work, this has to be continuous from 2 to 7. No breaks in the graph. And it's continuous. If you use the three-part definition of continuity that we learned in the last section, you would see that it's continuous at all values from 2 to 7. It is saying if you choose a y value between f of b and f of a, so something between 10 and 3, let's say we chose a y value of 8, does there have to be a place on here between 2 and 7 so that the y value has to be 8? Obviously, it's yes. If it's continuous and it goes as low as 3 and as high as 10, that means every y value has to be accounted for between 3 and 10. There's no way to skip over any of them because it's a continuous graph. It could go up and back down and back up. And when that happens, you could have more than one value that is 8. So let's read this again. If f of x is continuous from a to b, and in the little example we're doing here, we're saying continuous from the closed interval 2 to 7, and f of a, which we're saying is 2 right now, is less than y, and we gave the example of 8, is less than f of b, we gave the example of 10. So 10 is from here, 2 is from here, and I just chose a random y is 8. So clearly 8's between 2 and 10. Then there exists at least one value of x equals c, so there is an ordered pair in here someplace, some x value that would correlate to 8 on this, such that f of c equals y. Let me finish this out with, here we're saying there's got to be some y value, f of c, that corresponds to c in this. That's the intermediate value theorem, and hopefully that made sense to you. Let's look at some examples. Now these examples we're looking at down here, we're not going to get really, really deep into the intermediate value theorem. It's just trying to get a concept of, do we understand what, pray tell, is going on. Now investigate the graphs below to determine if the theorem is applicable for these functions on the specified intervals for the values given. This is a piecewise function. This is clearly a parabola, open interval on the right side. This is a line, and it starts with an open endpoint as well. So not using the theorem, just looking at the graph, is there a value of c on -5 to 2 inclusive? So we're looking at -5 to 2 is here, someplace in here. such that f of c is 2. So is there an x value that corresponds to a y value of 2? This line is y equals 2. I'm doing a lot more work for this than you would need to do. I'm just trying to get you to understand it. So does this graph touch someplace when the y value is 2? It sure does. It touches right here. What is the x value there? I'm not sure exactly. I mean, we could figure it out if we wanted to set this equal to 2 and then solve it. We're not going to do that. So is there a value of c? Yes, there is. And we're just going to say that c is between someplace between -5 and -4. Falls in here someplace, clearly. Looks like it could be -4.5-ish. It isn't, but it could be. And if I'm saying between -5 and -4, I probably should use open intervals, not closed intervals. All right, now we get a little bit deeper with the second question. Does the intermediate value theorem, so what we just learned, guarantee a value of c such that f of c equals 2 on the interval from -5 to 2? The answer is no. The reason it doesn't guarantee it, there's two parts that have to work for this. One, f of c has to be continuous on AB, inclusive. Two, f of c, the y value you're trying to find, has to be between the end values of your graph, where this is the highest and this is the lowest, and it's someplace between. So those are the two things we're looking for. So I was going to rewrite this a little bit, and this is how I'm going to rewrite it, the intermediate value theorem. We are allowed to call the intermediate value theorem IVT. On the AP calculus test, they will allow you to use capital I, capital V, capital T, and they will all know, the people that are grading it, it's the intermediate value theorem. So does it guarantee it? No, it doesn't. So let's state that it doesn't. Just saying no is not good enough. The intermediate value theorem, a lot of times when you're writing your answer for this, you're going to restate the question. Does not guarantee a value of c such that f of c equals 2 on -5 to 2. Reason? Because f of x is not continuous. On -5 to 2. Now, how could we have written this differently to be more consistent with how we wrote stuff in pre-calculus? We might, and in hindsight, I probably would have rather done this. Do step 1 and say f of x is not continuous on -5 2. Conclusion, the intermediate value theorem does not guarantee a value. It's how we wrote our answers in pre-calculus. Doesn't matter, I mean, whatever one's more logical to you. Second graph, which is the same graph, we're asked different questions. Is there value of c, and there's a typo here, on -1 to 5? So now we're looking from here to here, such that f of c equals 2. And no, this is not talking about the theorem, I'm just saying, looking at the graph, is there some place that the graph crosses the y value of 2 on this interval? And clearly not. No, there is no c such that f of c is 2. Does the IBT, the intermediate value theorem, guarantee a value of C such that f of C equals 2 on this interval? Well, the first thing you look at, is it continuous? And it sure is. F of x is continuous. On -1 to 5. So that's not the issue. The issue is that f of a, in this case, I don't want to use the letter, I want to use the actual number. F of -1, this is how it's supposed to be. F of -1 is supposed to be less than f of c, which is supposed to be less than f of 5. And we know what f of c is. I'll just write the number in there. It's 2. So what I would like to say, and this is a terrible way of saying it, so we're going to end up erasing this. This is not happening. And I think that's a confusing way to do it now that I've written it. So I'm going to end up not using that, and I will say this. F of c, which equals 2, is not between f of -1 and f of 5. That's what I want to say. This was confusing. So the conclusion that we can make from that, the intermediate value theorem does not guarantee a value of c such that f of c equals 2. All right, let's move on to the back, and this is re-emphasizing the intermediate value theorem. What two conditions must be true to verify the application of the intermediate value theorem? Well, as mentioned, f of c must be continuous on the closed interval. I'm sorry, f of x must be continuous on the closed interval from a to b. Keep in mind, these are x values. F of c is a y value, c is an x value, must be between f of a and f of b. All right, so the rest of these problems, every one of them, there are 4 or 5 of them, is applying the intermediate value theorem. For each of the following functions, determine if the intermediate value theorem is applicable or not and state why or why not. Then if it is, find the value of c that guarantees by the intermediate value theorem. All right, so here's what we do first. Determine, is this continuous? It doesn't have to be continuous every place, it has to be continuous on this interval. This is a rational function which has the potential of having a vertical asymptotes and holes. Holes are when things cancel. Factors don't cancel here. And vertical asymptotes happen when you have a non-canceling factor in the denominator. So this has a vertical asymptote at x equals -2. So that's the only place this is discontinuous, but the interval that we're using is -1 to 3. This discontinuity is not in this interval. So we can conclude that f of x is continuous on the interval that we are referring to. Is f of x continuous everywhere? No, but it doesn't have to be. It just has to be continuous on this interval. Next thing we want to check, we are simply checking, is this y value of 2/3 between the y value that you would get when you put -1 in to this function and when you put 3 into this function? We don't have a graph to know if that is true, So we got to do a little bit of work for this. We got to figure out what f of -1 is. We got to figure out what f of 3 is. And if 2/3 falls between those numbers, then the intermediate value theorem applies. If it doesn't fall between those, it does not apply. So we're going to have -1 minus 3 over -1 plus 2. That's -4 over 1. That's -4. F of 3, we're going to have 3 minus 3 over 3 plus 2. That's 0 over 5, which is 0. Once again, is 2/3 between these two y values? It is definitely not. So we would say f of c, which is 2/3, is not between f of -1 and f of 3. Conclusion, the intermediate value theorem does not apply. For f of c equals 2/3 on the interval from -1 to 3. Now, if we were asked a slightly different question, the same thing here, but then for f of c equals -1, the answer would be yes, because -1 falls between these numbers. How about -3? If y is -3, the answer is also yes. That number has to exist on here because this graph is continuous from -4 to 0. Let's try another one. It's the same function, it's a different interval. We already noted here, it's the same function. This has a vertical asymptote at -2. Well, when we try to do the first step, which is it continuous on the interval? -2, it's discontinuous. And in this interval, -2 is included. So we could say f of x is not continuous on -4 to 1, because it's not continuous at x equals -2. So we can just stop right there and we can say, therefore, the intermediate value theorem, you're allowed to abbreviate, does not apply for f of c equals 2/3 on -4, 1. Does that mean that there is no y value between -4 and 1 with a value of 2/3? It does not mean that. There could be. It just does not guarantee that there is. Something I should have mentioned before now, and it just slipped my mind, is the AP Calculus test is going to be composed of 4 parts. There are 2 multiple choice parts, and there are 2 free response parts. The multiple choice parts are broken apart into you can use a calculator and you can't use a calculator. The free response parts are broken apart in can you use a calculator and can you not use a calculator. Well, you can and you can't. You are to assume, unless I tell you otherwise, that every problem that we do in notes and homework, we are not using a calculator. Which leads me to number 3. There's a little calculator icon here, which means you're supposed to use a calculator. Did I include a calculator icon for every problem you're supposed to use a calculator in your notes and homework? No. Why didn't I? Because I make mistakes. So if you notice something, you think, hey, you should be able to use a calculator for this, let me know, and I will try to change that for the following year. All right, number 3, same directions. Speaking of continuity, is this continuous? It's an exponential function. It sure is. Is this continuous? It's the graph of cosine, which most years we do in pre-calculus. I'm not sure if we did last year or not. Hopefully we did. This is also continuous. If you're still unsure, put this in your calculator, and you can see this is going to be a continuous function. So we can simply say p of x is continuous for all values of x Well, I don't need to say all that. I can just say p of x is continuous on this interval. Continuous at all values is certainly continuous on this interval. Number 2, is 5 this y value between the y values you would get here? I don't know. We got to figure it out. So p of -2 and p of 1. Now, when you do this, when there is a calculator involved, this is all the work that you have to show, that you're putting a -2 into this. So what you can do is you can go to your y1 in your calculator. You can type in this function, e to the x plus 2 times cosine of x. And then you can go to your table. Make sure you set your table up first, do second table set, and then choose your independent variable to ask. And then you can just type in when you go to your table, x is -2, and you should get something like -1.131. And you should get, for p of 1, something like 10.852. It's all the work you got to show when you have a calculator. You do have to write this down. I mean, that's the work that you show. So is 5 between these two numbers? It sure is. So we can say that simply by saying p of 1 is less than p of c, which is, and I'm going to say what p of c is equal to, which is 5, which is less than p of 1. This part here may not be entirely necessary on the AP test, so I'll leave that as optional for you folks. I kind of like it though. Therefore, the intermediate value theorem applies and guarantees a value of C on -2, 1 such that f of C equals 5. Now we were supposed to, the direction said, if it does guarantee a value, find that value. Hopefully you wrote smaller than I. Not a ton more work, but we got some more work to do. So we got this function that you already have typed into y1. Good, leave it there. What we want to know is, if you put 5 in for y, what is the x value going to be? Now you're likely going to find that there are lots of answers for this. This is a cyclical function which repeats itself, so there could be lots of answers. We only care about the interval from -2 to 1. So what you would do is you go to your calculator, you set your window, so your x min is -2, your x max is +1, getting those numbers from here. And then you type in, you already got y1 as this function here. And then you put into y2, 5. Then you do second calculate intersect. And by the way, I do want to change something, what I just wrote down here. We're looking for a c value, so I'm going to change these x's to c's. Is it the end of the world if you leave it as an x? Not necessarily, but when we answer the question, it needs to be a c. Anyhow, see where they intersect on the interval from -2 to 1, and I believe that you will find that c is -0.334. Reminder, we use 3 decimal places in AP Calculus. All right, number 4, no calculator, so we can't use a calculator. Is this graph continuous? That's the first question. Is it continuous from -1 to 1? The only place this is discontinuous is at x equals 2, because there is a vertical asymptote there. That's not in this interval. So we can say f of x is continuous on the interval from -1 to 1. Now in the homework, I might be writing down stuff like, hey, f of x is only discontinuous at x equals 2, which is not on the interval, thus it's continuous. As far as your work goes on the AP Calculus test, this is all you got to write. 2. Is this y value of negative 1/2 between the y values you would get if you plug these numbers into this? I don't know. So let's figure it out. We're not allowed using a calculator. There's no calculator symbol. So we have negative 1 over negative 1 minus 2. That's negative 1 over negative 3. That is a positive 1/3. If we put a 1 in for this, we're going to get 1 over 1 minus 2. That's 1 over negative 1, which is negative 1. Is negative 1/2 between a positive 1/3 and a negative 1? It sure is. So I'm going to say, so I'm going to list the one that is smaller first. This is f of 1. F of 1 is less than f of c. F of c is negative 1/2, which is less than f of negative 1. Now the order of this matters once again. You got the bigger thing on the right, the smaller thing on the left. So that matters. So our conclusion from this, the intermediate value theorem guarantees a value of c on the interval from negative 1 to 1 such that f of c is negative 1/2. Now we're supposed to find that value. So we simply take the function that we were given. We replace the y value with negative 1/2. And once again, we're trying to find a c value, so I'm going to also replace the x's with c's. If you don't do that, it's fine, but your final answer needs to be a c value because that's what it asked for. So I'm going to multiply both sides of the equation by c minus 2 and 2 to get rid of my fractions. On the left, the 2's cancel. On the right, the c's minus 2's cancel. So on the left, I'm going to get a negative c plus 2 when I distribute this negative 1 to each of these. And on the right, I'm going to get 2c. If I add a c to both sides, I get 3c is 2, so that c is 2/3. So that is the c value. We got one more. One more. Wow, the spacing on this is a little whack. This is my function, including that negative 2. So is this continuous? Well, this is an exponential function. Exponential functions are always continuous. You need to know your parent graphs. F of x is continuous at all values, so it's certainly continuous on the closed interval from 3 to 5. 2, we got to figure out what the y values are of the endpoints of our interval. So non-calculator. So we got f of 3, that's negative 1/2, and then we have negative 3 plus 3 minus 2. This should be pretty easy. So it's a negative 1/2 to the 0 minus 2. Ending to the 0 is 1, so we have negative 1 minus 2, which is negative 3. Not so bad. Put a 5 in for this. We have a negative 1/2. We have a negative 5 plus 3 minus 2. That is a negative 1/2 to the negative 2 minus 2. Going to have to write smaller here, chillins. If I want this to not be a negative exponent, I got to reciprocate this. So it's going to be negative 2 squared minus 2, which is negative 4 minus 2, which is negative 6. So is negative 4 between negative 3 and negative 6? It sure is. F of 5, which is the smallest number, is less than f of c, which is negative 4, which is the middle number, which is less than f of negative 3, which is the biggest number. Biggest meaning on a number line. Therefore, the intermediate value theorem applies and guarantees a value of C such that f of C equals -4. So to find that value of C, we're going to take our function Now, if at some point you were screaming, why didn't you change this so that the base was bigger than 1? You can do that. We're not graphing it. We're not asking for transformations. That's why I didn't do it. If you want to do that, that's cool. You can. So the y is -4. We're looking for the C value that makes that happen. And add 2 to both sides. Going to divide both sides by -1. I'm trying to get this base 1/2 by itself is what I'm trying to do. Well, the base to the exponent by itself. Now from here, tell you what, let's do what I said earlier. Let's make this base bigger than 1. It's going to make our lives easier. In fact, I unwittingly made our lives super easy. We had a property for exponents last year that said if you have an equation, which we do, in which you have one term on each side, which we do, and each of those have the same base, which we do, you can set the exponents equal to each other. Therefore, 1 equals C minus 3, and we get C is 4. Boom, done. All right, that concludes the notes. Please do the homework for section 1.7.